Hi, in this lectures, we are going to study a number of topics. First, we will discuss the design of the shaft used to transmit power. Second, we will develop the equation to determine the angle of twist in a shaft. And finally, we will discuss a procedure to analyze statically indeterminate torque-loaded members. To understand the first topic, let us review the equation to determine the work done by a torque that you might have already learned. For that, let us replace a torque T by a couple of force as shown on the screen. The reason for that is we already know how to determine the work done by a force when it moves an object a certain distance. So let's say the couple of force F rotate this disk an angle d theta as follow. Then the work done by this couple is calculated by this equation, where ds is the distance that you can see on the screen. Since ds can be calculated from d theta, we can rewrite the equation like this and this. Finally, you can see the equation to determine the work from the torque and the angle d theta. In other words, if a torque rotates an object a certain angle measured in radians, the work done by the torque is calculated by multiplying the torque with the angle. That being understood, we will now see how we can design a shaft used to transmit power as shown on the screen. To be specific, given the power that the shaft transmits, the angular velocity or the frequency of rotation of the shaft, we need to determine the torque the shaft is subjected to so that we can design it. So let's see how we can proceed. If you remember, the power is defined to be the rate at which work is performed, or in other words, the work done per unit of time. That means we can write the power that the shaft transmits to be. From this equation, we know how to determine the torque given the power, the angular velocity, or the frequency of rotation. Now, knowing the torque a shaft is subjected to, we can easily design the shaft based on the knowledge that we learned in the last lectures. Let us review the parameters in this equation. C is the radius of the shaft. J is the polar moment of inertia of the shaft's cross-section, which can be calculated from the radius C. T is the torque we just determined, and tau allowed is the allowable shear stress of the material of the shaft. I suppose you will be able to make a proper adjustment to the desired equation when a hollow shaft or a tube is to be used. In that case, we will have two parameters to determine the inner and outer radius. Now we will discuss the second topics of these lectures, where we will develop the equation to determine the angle of twist. For that, let us consider again the shaft and the element that you saw in the last lectures. As you can see, I added some parameters that we will use in the analysis. Specifically, the capital letter L is the length of the shaft. The lowercase l is to define the location of the red element, and dl is the length of the element. So let us zoom in the element. This is the geometries before deformation. Now let us see again the deformation when a torque is applied. We would like to determine the angle of this phi given all the needed information. The idea here is we will first develop the equation to find the angle of twist d phi of the length element, and then integrate that equation over the entire length of the shaft. If you remember, we did the same before to determine the displacement of a bar subjected to an axial load. That said, let us develop the equation to find angle d phi. First, as you can see, d phi can be calculated from the length dl of the element, maximum shear strain gamma, and the radius of the cross section at the location of the length element. If we continue doing the math, we will finally end up with this equation to determine d phi, the angle of twist of the length element. As I just mentioned, now we just need to integrate this equation over the entire length of the shaft. You can see that in the case T, G, and Z are constant over the length of the shaft, the angle of twist will be calculated by a very simple equation as follows. At this point, I think you start seeing the similarities between the equation to determine the angle of twist and the one to determine the displacement of a bar subjected to an axial load. That said, if a shaft consists of multiple segments as shown in the slide, we can do the same as before when we learn about member subjected to axial loads. Specifically, first we will divide the shaft into segments of constant torque, constant modulus of rigidity, and constant polar moment of inertia. Then we will determine the angle of twist for each segment and sum them up. As you can see, the shaft on the screen can be divided into three segments. If we want to determine the angle of twist between the two ends A and D, we can apply the following equation. However, if we are asked to determine the angle of twist between D and B, the equation to be used should be the following. Now, a very important note when we use this summation is we should follow the sign convention to avoid confusing ourselves. That said, the right-hand rule is commonly used to determine the side of internal torque and the angle of twist for each segment of the shaft. After we use the method of section to cut through a shaft, the right hand will be used on either one of the portions to determine the side. Specifically, we will let the right hand fingers curl in the direction of the torque. Then if the thumb is directed outward from the shaft portion, the sign will be positive, otherwise the sign will be negative. Now we will discuss about statically indeterminate torque-loaded members, the last topic of today's lectures. For that, let us look at the shaft on the screen, which was fixed at two ends. You can see that if a torque of 500 Newton meters is applied at B, we will not be able to find the support reaction at NA and NC based on the equilibrium equations. To illustrate, let us replace the supports by the reaction and write the equilibrium equation. Since we have two unknowns with only one equation, we will not be able to find the unknowns. If you remember, this is why we call the problem statically indeterminate. To solve it, we need to establish one more relationship between the two unknowns, TA and TC. As you may guess, since NA and NC are fixed, The zero angle of twist between C and A will help us obtain that relationship. That said, let us write the equation to determine the angle of twist between C and A. To continue, we need to determine the internal torques in segment AB and segment BC. For that, we have to use the method of section. Let us section through the segment AB first and keep one portion to draw free body diagram. Why we can see right away that the internal torque in segment AB is equal to the unknown torque TA. We will use the right hand rule to determine its sign. As you can see, since my thumb is direct inward the remaining shaft portion, the side of the internal torque in segment AB will be negative. Now let us look at the entire shaft again and section through segment BC. Keep one portion to draw free body diagram. Like before, use the right hand rule to determine the side of the internal torque in segment BC. This time, since my thumb points away from the remaining shaft portion, the side of the internal torque in segment BC will be positive. Let us go back to the equation we were working on before. Now we will replace the internal torques in segment AB and BC by the two unknowns based on what we just found. Plug in the value. As you can see, another relationship between the two unknowns TA and TC has been found. Now from the two relationships, the equation 1 and 2, we can easily find the two unknowns. You can see that the procedure is exactly the same as the conventional method for solving statically indeterminate axially loaded members. I suppose you might want to try something similar to the first method for solving this problem. If that is the case, please let me know whether you obtain the same result. That's all for today. Thank you and see you in the next lectures.